Okay, so welcome to my talk about our paper called HydraViT, Stacking Heads for Scalable Vision Transformer. I'm Janek Haberer, and I'm from Kiel University in Germany. Yeah, so as I hope most of you should be familiar with vision transformers, they are currently the state of the art in computer vision. I mean, they are still clashing with convolution, like CNNs and also some similar architectures, but I looked at the current leaderboards or whatever, and right now the transformer architectures are still sitting at the very top, getting the very best accuracy on data sets like ImageNet. And yeah, essentially they are built on this attention mechanism, which is the core component of them, that allows them to capture global relations across the entire image, which convolutions usually can't do. And yeah, they are basically able to be scaled up to billions of parameters, although they need a lot of data. And usually we deploy specialized models on devices with varying constraints. So assuming we have different devices, I mean, these are just example numbers, not the actual reality, but assuming we have like maybe some servers that have quite, like a lot of RAM, for example, and then desktop PCs are somewhere in between, and mobile phones, which have much lower resources, we need to devise specific models that work on these devices. So for example, on the cloud, we might be able to deploy an architecture like ViT base. Then on our desktop PC, maybe something like a ViT small. And then on our mobile phone, we have models like ViT tiny. Again, this is just as an example, right? But you should get the idea. And the additional problem here is that the attention mechanism is quite RAM hungry. It requires quite a lot of resources. But yeah, luckily the base ViT models, we have like at least a few of them for different constraints, for different devices, which is nice. But wouldn't it be nice if we could just have one single model and then, yeah, basically take, like we train one single model, one large model, and then we deploy subsets of these on the smaller models, or on smaller devices. So basically we train one large model, and then we train it in a way that we can extract these smaller models and deploy them on smaller devices, instead of training one specific model for the different constraints. Especially because larger models, they have quite minimal accuracy differences. So yeah, training each one from scratch, it just takes a lot of resources and is quite expensive. And actually, in our case, we can even extract more than just these 3 models, which are supplied by the original ViT authors. We can even get up to 10 models, for example, just by doing one training run. And yeah, furthermore, we noticed that the original vision transformers are perfect subsets of each other, which inspired our design. So we can see that the amount of layers, or well, to be more correct, the amount of transformer blocks is the same for all of them. For ViT tiny, for small, and for base, it's always 12 blocks. And the only thing that really changes is the embedding dimension and the corresponding amount of heads that you use in the multi-head attention. And yeah, this is basically an interesting observation that these are perfect subsets of each other. So what we are basically, what we're trying to achieve, and what we did achieve, is to unify this into just one model, right? So we basically train a model, let's say with the base architecture of ViT base. And we train it in a way that we can then also run it as a ViT small by just using the corresponding weights for this ViT small model, for example, right? And one thing to note here as well is that if we don't do it in a, like if we just take a ViT base model and just run it as a ViT small model without doing anything, like we just take the weights of a ViT base model, then the accuracy is quite bad because we didn't train for ViT small subset of it, right? So this is basically what we have to do. Yeah, so now we need to figure out how do we train this? And here there's an interesting paper called Matformer. It's not the only one, but it's one paper that basically also tries to solve similar problem. And what they use is something called Matryoshka learning. So you can see it here on the right. Oh, sorry. Basically, it's, oh, there's the overlay clashing with me, sorry. It's basically here on the right in the MLP block. And it's only in this hidden layer of the MLP block in the transformer architecture, where they, essentially, where they nest the neurons of the layers and order them. So we can see that the red box is basically a subset of neurons, which is a subset of the orange box, of the yellow box, and the blue and the yellow box. And this way we have an order on these neurons and can run these subsets. And then for the training of that, basically they just use a random sampling of these subsets. So we have different configurations. And then, for one batch, we run it at 25%, and then for one batch at 50%, and so on. And through that, over enough epochs, we kind of make sure that each of these subsets achieve a certain accuracy. So one thing here is that, as you can see, they just do the MLP hidden layer. So they ignore the attention entirely. And they also ignore everything in between. So obviously we have the embedding dimension that goes into the MLP. That one is also fully sized in this case. And this is what we also wanted to tackle, right? So we wanted to make everything scale down. And for that, we now basically modified each layer. So starting with the MLP, well, that is something that we can already see from Matformer essentially. So we adjusted each operation in the code to be able to run them at a smaller size, at a subset. Then we did the same for the layer normalization. And then the final thing is the multi-head attention, which looks a bit more complicated. So here we have the query, the key, and the value extraction. So you can see that we here also essentially always take out the leftmost subset. So in all of these, we take out the same sized subset, and then we multiply them. So what then happens is essentially that we also group them or reshape them into the corresponding head shape. So we don't extract half of the embedding and then still group it into 6 heads. We actually keep this embedding per head dimension constant. So for each head, we still keep the 64 input neurons, as is the case for ViT small, tiny, and base as well. So this is a very important thing. This is something that not everyone has done. Some of them keep the amount of heads just at 12 essentially if they start with the base architecture, and this leads to some inconsistencies. Okay, so now we have shown how we basically adjusted the attention block as well, layer normalization, and the MLP. So basically now we have our architecture that we can now run at smaller subsets. And the way we implemented it now means that we can actually emulate a smaller subset perfectly. So what we can do is we can initialize a HydraViT with the ViT base architecture and then load the pre-trained weights of a ViT small and then run it at our 6-head configuration essentially, which is the ViT small configuration. And then we actually do get the exact accuracy that you would expect from a ViT small pre-trained network. This is not the case for Matformer, for example, because they only do the scaling in the MLP block, right? So this is basically what we were trying to achieve, and this is what we now have. So this is really nice because now we can also benefit from initializing with a small model that is pre-trained and then just learning the heads on top. So we basically don't have to train from scratch. Yeah, and now for the training, well, should be kind of obvious now, but yeah, basically we do stochastic dropout training. So essentially for each batch, we randomly select the value k, and then we train only the subnetwork with the first k heads. So you can see it here on the right. So in the first batch, we selected the value 4, so we trained the subset with 4 heads. And then in the next iteration, we train it with 9 heads, and so on and so forth. So here we can see that in iteration 5, this is with 3 heads. This would be like ViT tiny. And then in the 6th iteration is the full model, so it would be like ViT base. But you can also see we do all of the ones in between. So we don't have to restrict ourselves to ViT tiny smart base. We can also go for models in between. And as a result, what happens is that the initial heads, the smaller heads, they get more gradients. They are more involved in the training. So in a sense, they are more important. And vice versa, the later heads are not that important. They are just there to inch out a few more % of the accuracy, right? Whereas the first heads are trying to do the major lifting. Yeah, and with that, we come to the evaluation. For the data sets, we trained everything on ImageNet 1K and evaluated it on ImageNet 1K as well as some other variants. So we have ImageNet V2, ImageNet R, A, Sketch, and Real. And of these, I will be showing the first, like some results for the first 3. For the remaining ones, please check out the paper where we have all of the results. Also check out the appendix. So there's quite a lot more results in the paper. Then for the metrics, we evaluate accuracy versus throughput versus GMACs and also RAM. In this case, RAM, I will also not be presenting. This is also in the paper though. And finally, for the baselines, we have Matformer and then also Dynabird and SortedNet, which I will quickly introduce now. So for Matformer, you have seen essentially they have a flexible MLP hidden layer, but they keep the attention fixed and also the entire embedding dimension essentially, right? It's only the hidden layer that they adjust. And they also only evaluate on natural language processing, so on other transformers than vision transformers. In Dynabird, they do adjust the multi-head attention as well, and also the MLP, but they keep the intermediate embeddings fixed. So basically, you stay at, let's say, 768 values or neurons for one embedding. And then when you go into the key query value, then you reduce the size. Or if you go, I believe for the MLP, I'm actually not sure if it was only for the hidden layer or also for the entry layer, but they always go back to this initial embedding size. So they don't fully size it down, which kind of also means if you look at memory, you kind of need to fit the largest operation. So if you don't scale everything down, then yeah, it might mean that you need more RAM than you could if you scale everything down, right? So Also, it's only for NLP as well. And then sorted net, they have flexible embeddings everywhere. So from the very beginning, like between every layer everywhere, just like we wanted. But for them in the attention block, they kind of don't couple the attention heads to the embedding dimension. So they either would keep it fixed at the maximum size, so for example 12 if we take a base architecture, or if they would include the attention scaling, then it wouldn't be coupled to the dimension. So they would go to 50% dimension, but the heads could still stay at maximum or go down to 25%. They don't keep this ratio fixed, and this is something that we argue is very important to kind of keep this somehow aligned and otherwise it makes the attention very chaotic in each of the runs, because you every time have like a different size for the heads, and it makes everything messy. Also, they only evaluate on CNNs or NLP again, so there hasn't been that much on vision transformers so far. Other than that, if you remember, we said that in HydraViT, we kind of have these perfect subsets still available. We can still emulate these smaller subsets. This is not the case for these works. So yeah, for the first two, it should be obvious because they don't scale everything down. And but also for sorted net, because it doesn't really have the attention heads coupled to the embedding dimension. So they kind of lose this ability that we still have. And yeah, now for the results. So first, we are looking at a comparison of our accuracy, which is on the y-axis, compared to the GMACs on the x-axis. And with the stars here, you can see the DIAT baseline. So here you can see a DIAT base model, here the DIAT small model, and here the DIAT tiny model. And then, yeah, for HydraViT, we have, I believe, these two lines here. The gray one is with 800 epochs. The blue one is with 300 epochs. And then sorted net is the orange line here, slightly below. So we can see that if we train HydraViT for 300 epochs and sorted net obviously also for 300 epochs, we get slightly better accuracy at each step, right? So at each step we have a slightly higher accuracy compared to the GMACs. When we go a bit more to this right part here, so to the, I would say like where we need a few more GMACs, we can zoom in here. We see that Matformer, while it is constrained to this smaller area, so it's not really able to run at less than roughly 8 GMACs, it does beat this blue line, so our 300 epoch HydraViT, and even our HydraViT that we trained for 800 epochs. But we argue this is mostly the case because they are restricted to this larger area. They don't change as much in the network. They are not that flexible. So we did another test where we constrained HydraViT to just go for 9 to 12 heads. So we can see 9, 10, 11, 12 heads, the 4 dots at the top. And then we have a similar range as Matformer with respect to GMACs, but we do beat them out on accuracy by quite a bit. So yeah, we argue that our approach is more efficient. Yes, they do have more models in between, but they are not that useful. Yes, and then for the throughput, which sometimes is maybe a bit nicer of a metric because GMACs doesn't always tell the whole story. This is done on an A100 for all of the models. And yeah, here actually the gap is much larger. So if you compare to sorted net, we have here at this point, like at around 6,000 samples per second throughput, we have a near 7% accuracy gap So we have nearly 7 percentage points better accuracy, yeah, which is quite a lot. And yeah, once again, if we train our model for even more epochs, we can see that we consistently improve our metric and are even nearly able to beat all the standalone models. Even though, keep in mind, we are training 10 models in parallel and not just 3, right? So that is also quite nice. Yeah, and then also zoomed in, same story as before. So Matformer, the red line here in this smaller space, it doesn't really reach a higher throughput because it doesn't change the, like, it didn't change the attention block. Yeah, they are able to beat HydraViT with only 300 epochs, but if we again restrict ourselves to 9 to 12 Hz, so a similar range, then we are able to beat them as well. One thing also to note here, for all of these experiments, we initialized with a DIAT-tiny model, but we also did all these experiments from scratch. For that, once again, I would refer to the paper for the full results, so you can check them out there as well. Yeah, and now I want to take a look at another small thing. So as I said, reaching the DIAT-tiny, DIAT-small, and DIAT-base accuracy with one of our HydraViT models is quite difficult. We are training for 10 submodels instead of just 3. So what we now want to try is what happens if we just go for 3 submodels. So this is what we do here. So at the bottom, you can see the accuracies for the respective DIAT models. So we have for DIAT-tiny 72.2, for DIAT-small 79.9, and for base 81.8. And now we take our HydraViT with the base architecture, and then we train also for small and tiny, so for 3 and 6 heads. Once again, it's initialized with the DIAT-tiny, which means technically we are getting a 300 epoch head start. So usually like these models are all trained for 300 epochs. So in total, it would be 900 epochs to get these 3 accuracies at the bottom. And what we do now is we train a model, our HydraViT, for 300 epochs. So technically in total, we are now at 600 epochs. And we can see that, yeah, our tiny accuracy is already better, which makes sense because we initialized with tiny. And our 6 head is quite close, I would say. And 12 heads is, well, kind of far off. What we can do now is we can increase the amount of epochs. And yeah, slowly but surely our results get better. We get higher accuracy. So now with 500 epochs, we would be at a total of 800 epochs training compared to the 900 for the 3 individual models. But we're still, I mean, now we're beating at least also the small model, but we're not the base model, right? So we had some other ideas that we wanted to try. These are ideas that we found didn't make too much sense to try on having 10 heads or even more heads, although potentially there is also some room of improvement and it could be used in some way or the other. But at least here, we also thought, okay, weighted sampling, what about that? Like right now, we're just doing uniform sampling. We just choose any at random. But maybe we can skew this a bit, and because we see that the larger models, the 12 head model is the one that needs improvement, we now skewed this a bit towards the base model so that it gets sampled more often. And what we see then is that, well, first of all, compared to the respective not weighted sampled HydraViT, that now the tiny accuracies are worse, which is exactly what we would expect, right? Because now we are sampling these less often. The small model is somewhat comparable, and then the 12 head one is now actually, yeah, quite nicely improved compared to without the weighted subsampling. And then we thought of another idea to take it even a further step, is separate classifiers. So basically having a different classification head for each configuration. So in this case, we would have 3 different classifier heads, 1 for each configuration. And if we do that without the weighted subsampling, so now we compare this block to this, to the first block, we see that in most cases we get a higher accuracy, although here we can see that we do get a worse base accuracy, which it's like a maybe like a disadvantage of it, that now each classifier has less gradients because we don't have a shared classifier head anymore that gets all of the gradients. But on the other hand, they are able to specialize more for this configuration at a small cost. And if we combine both, actually, we get what, well, one might argue this very bottom row might be the closest result to trying to beat all of these single models. Where we beat at tiny and small, the respective D at tiny and small, but then at the base configuration, we are just very, very slightly off. So in a sense, with this, we can achieve one model, like one set of weights that has these subsets in the weights that we can also run D at small and tiny, and not have to have separate models for each of these configurations. Then one other small outlook is confidence. I mean, we have here 2 sample inputs, and then we can see like each column is basically one configuration. So we can see we have 1, 4, 3 heads, which would be like tiny, 6 heads is like small, and then 12 heads is like base, and then all the ones in between as well. So we can see like the attention essentially, or the most influence on the classification, and then also here we can see the classifier probabilities. So especially here, the first row for this Walker-Hund example, we can see that with a 3-head model, actually we misclassify this. So it would be classified as a whippet, which I did look up is a different type of dog. And then once we go to a 4-head configuration, we actually already get the correct classification with the Walker-Hund, but you can see it's only very, very slightly correct. So it's barely correct. It's not very confident in its decision. And then as we increase the amount of heads, this confidence essentially increases. And then also here at the bottom, while the 3-head configuration is already in the very, it's already correct, it is not very confident. And then, at 6 heads, we kind of reach a very, nearly the plateau. And after that, it doesn't increase much anymore. The attention maps themselves are a bit difficult to interpret, I would say. I mean, one could argue that at some point it's able to focus on maybe the more important features in a way, or maybe at some point it also focuses on some not as obvious traits, but it's mostly about the confidence here, which I think is very interesting, seeing that the more heads we use, the higher the confidence, mostly. And then for a final quick outlook on the evaluation here. So I also said that we tried it on other ImageNet variants. So we didn't try just on ImageNet 1K. We also we trained it on ImageNet 1K, but we also validated it on the other ImageNet variants. So these are some augmented data sets, or partially also completely different image data sets that are classified according to the ImageNet classes. So here we have ImageNet V2, once again comparing accuracy to GMACs. And basically we see a very similar picture to the normal ImageNet 1K results. And then we also have ImageNet A and ImageNet R. And yeah, well, I mean, there are some inconsistencies we can see here. Like, for example, Metformer is able to beat HydraViT even with the 9 to 12 head combination in some cases, but then in other cases, this is not true. So yeah, certainly there are some data sets where there might be some slight overfitting or similar stuff involved. Maybe there are still some ways to improve it even further, but we didn't really investigate this too much to figure out how we can also fix this. For the remaining results, so also for the throughput and the other image invariants, once again, I refer you to our paper where we have everything. And with that, I come to the conclusion. So we presented HydraViT. It basically sorts the attention heads and the embeddings based on importance. It offers a flexible inference based on your hardware availability. And it is able to outperform the baselines by up to 7 percentage points at the same throughput. And yeah, I invite you to also check out our code, which should have everything you need to reproduce everything and evaluate against. If there are any issues, feel free to reach out, contact us via email or via an issue. And yeah, thank you.